This week we'll be starting our last unit, which is looking at astronomy. So first of all, what is astronomy? Well, it's the study of what is in space beyond the Earth. So when you look into the sky, what are you seeing up there? What are those things? And how do they behave, and why do they behave in that way? That's really what astronomy is trying to look at. And along with it comes a number of other questions, right? Because you start to ask, how was the Earth formed? How was our solar system formed? People who study the sky are called astronomers, right? So the people that are trying to answer those questions. Now, the first telescope wasn't invented until 1608, so it's been about 400 years that we've had telescopes. So it really wasn't until 1608 that we could start to collect some sort of data on this stuff, on what is around the Earth, what else is out there. So Galileo was one of the first scientists. He was both a scientist and a philosopher who was able to start taking measurements and taking observations using a telescope. So he's known as one of the founders of the scientific method because he was able to take an idea and then go out and measure something, take some observations, and then see if it matched up with that model that he had. So in 1609, he was the first one that was able to gather evidence to prove that the sun was actually the center of our solar system, and that the Earth, along with the other planets, was orbiting the sun. And at the time, that was a very controversial topic. And in fact, he was arrested and his work was banned by the church at the time because that was not an accepted belief. And it wasn't until about 200 years later that his books were actually published. So astronomy can be a very fascinating topic because it's looking at a large scale of things, right? Not only what are the things in our solar system, but what are the things beyond that in our galaxy and in our universe? And how was our universe created? So along with those scientific questions also come a lot of philosophical questions. But we're really focusing on what can we collect data on? Because if you can take an observation and you can collect that data and compare it to a model, that's when you can start to actually prove things. All right, so before we get into anything, we're just going to do kind of a quick little cosmic quiz to see what you know. So at this point, I'll get you guys to pause the video, see if you can go through and see if you know any of these 10 answers. If you don't know any, no problem. If you do, awesome. So see if you can pause the video and try those right now. All right, so let's see what you got here. So first of all, how old is the Earth? I mean, the year is 2000, but the Earth has been around a lot longer than humans have been recording time. So the Earth is about 4.5 billion years old. And we've used radioactive decay in order to confirm that. So we've looked at how certain atoms are breaking down in material in the Earth, and we can use that to kind of track back and figure out how old the Earth is. What is a shooting star? It's really just a piece of rock that's burning up in the atmosphere. Remember, Earth is surrounded in this blanket of air. And if something is moving really fast and it hits that air, it starts to warm up, and if it's going really fast, it'll burn up. So that's what a shooting star is. What is the moon made of? Mostly volcanic rock. When was the last time humans set foot on the moon? So last time was in 1972, and the first time was in 1969. That's when the Apollo missions were. Number 5, name the 2 planets that are closest to Earth. Venus, which is closer to the sun, and then Mars, which is further away. Have humans visited these planets? Humans, no. We have sent probes to both Venus and Mars and landed probes on both Venus and Mars, but we have not sent humans there. We've only sent humans to the moon. How close is the nearest star? Kind of a trick question. The nearest star is our sun. And the sun is about 150 million kilometers away. So even that is a huge distance. What is a galaxy? If you heard of the Milky Way galaxy, a galaxy is just a collection of stars and planets and moons and gas and dust. So a bunch of solar systems, really, right? Because most stars have planets orbiting them. And if you take a bunch of those and put them together, you have a galaxy. And they're held together by gravity. So anytime something has mass, it weighs something, it starts to pull on other things that have mass and weigh things. And that's called gravity. How big is the universe? It's huge, and we don't really know exactly how large it is, but we do know that it's still expanding, and it's getting larger over time. Is there life in our solar system other than on Earth? Not that we know of, right? We've sent a number of probes out there into our solar system. We've landed on, Mars and Venus and some asteroids and a comet, and so far we haven't found any indication of life. What about in the universe? Is there other life in the universe? Once again, we don't know. I mean, we haven't been able to get past our solar system, right? The furthest probes that we have are the Voyager probes, and those are slightly outside of our solar system. They are nowhere near another solar system. And we will lose contact with them far before they ever reached another solar system. So the reality is we really haven't been able to look that far. But we do know that the number of planets in the universe is unimaginably large. I can't really give you an example of how large it is because that's how many there are. So is there a probability that at least one of those planets is in a condition similar to Earth where it could have water and an atmosphere and possibly life? Probably. Will we ever be able to reach it or communicate with it? Possibly not. Last one. What is the difference between astronomy and astrology? So astronomy is a science. It's a hard science. It follows the scientific method where you can make a theory, go and collect some data, see if it supports your model, make sure that it's a repeatable experiment, and then come up with some sort of conclusion. Astrology is not a science. So astrology is really it's the same as like a psychic. So people will talk about, oh, they've made predictions based on the movement of the stars, but that's no different than reading tea leaves or tarot cards. It's not a science. It's just essentially what a psychic does. All right, so hopefully you had a chance to try those out. Maybe you knew one or two of them. If you did, awesome. All right, let's get into a couple of the lesson for today. So first of all, well, when you start looking into the sky, what are some of the things that you can see? Well, first of all, you can see luminous things. So these are things that produce their own light. These are stars. So for example, our sun, there's currently a chemical reaction happening in our sun, and it is producing a lot of heat and light. It's releasing a lot of energy, and we can get that light, right? That light reaches Earth, and it allows life to exist on Earth. So those luminous things that we're seeing in the sky are all stars, similar to our sun. Some of them are bigger, some of them are smaller, but every star that you see is essentially a sun. Sometimes people will look at kind of a pattern of different stars that they see, and they call those constellations. So those have been useful in the past for navigation, right, for figuring out where you are. Right? Some of the most popular constellations like the Little Dipper or the Big Dipper. So sometimes if you're looking for something in the night sky, you might use those constellations to guide you. Other things in the sky, well, we can see other planets. So if it's a nice clear night and you know where to look, you can see Venus or sometimes Mars. Now, these are other planets, and those planets are non-luminous. They don't make any light, but they would reflect light. So when sunlight comes in, it'll bounce off of them and come back to Earth, and that's why we can see them. So we're really seeing this, the light from the sun that bounces off of it. The same as our moon, right? The reason we can see the moon is because the sunlight is bouncing off of it or reflecting off of it and coming back to Earth. Other things, well, we just mentioned a moon, right? So we have the Earth's moon, but many other planets in our solar system have moons, and some of them have a bunch of moons. Next one, a comet. So a comet is a frozen core of ice, gas, and dust. And a lot of the time, these are on very large orbits, where they'll only come near the sun sometimes every 10, 20, 100, 500 years. And when they come near the sun, they start to warm up and they melt a little bit, and they'll leave kind of a trail of dust and maybe water behind themselves. And you can actually see that in the night sky. So those are called comets. So one of the most famous one is Halley's Comet. A meteor. So a meteor is matter, so some sort of rock, for example, from space, that burns up when it enters Earth's atmosphere. So when we were talking about the shooting stars before, that's really just a chunk of rock that's hit Earth's atmosphere, and it gets really hot and it burns up. And the majority of matter that hits Earth does just burn up in the atmosphere. It doesn't reach the ground. But occasionally a large one will. And last one are asteroids. So once again, these are generally rocks, but they are continuing to orbit the sun. So they don't get near the Earth. They don't crash into anything. They just keep orbiting the sun. And there's actually a belt of a whole bunch of asteroids past Mars. So past Mars is this thing called the asteroid belt. So those are generally the main things that we see in the night sky, and that back in 1608 Galileo was looking at in the sky. Now, we'll look at a couple diagrams here in a minute, but we need to talk about some units, because when we start looking at the solar system and different galaxies, it doesn't make sense to use kilometers anymore. So for example, here's a little chart that shows the distance to a couple other the distance from the sun to a few other planets. So for example, Earth is about 150 million kilometers from the sun. So kilometers is not really a useful unit because these numbers get really cumbersome to use, right? Oh, Jupiter is 778,570,000 kilometers. That number is very awkward to use. So we instead use something called an astronomical unit. So 1 astronomical unit is the distance from the sun to the Earth. So we just said, let's make the distance from the sun to the Earth 1 AU, 1 astronomical unit. And then we can compare everything else to that. So for example, Venus is 0.72 astronomical units. So it's closer to the sun, right? It's less than the distance from Earth to the sun. Mercury is only 0.39. It's quite close to the sun. Mars is 1.5 AUs, so it's 1.5 times as far from the sun than the Earth is. Neptune is 30 AU, so it's 30 times the distance that the Earth is from the sun. So anytime we're looking at the solar system, generally we use astronomical units. It's just a much more useful and convenient unit to use. And all it does is just compare back to the distance that Earth is from the sun. Now let's say that you wanted to look beyond the solar system, because the solar system, even though it's very, very large, and we're only beginning to explore it, on the scale of the universe, it's tiny. So as soon as you start looking past the solar system, so now you're looking at maybe nearby stars or galaxies, or even beyond that, clusters of galaxies, now you have to start using a bigger unit. And we use something called a light year. So a light year is the distance that light travels in 1 year. So let's say you took a laser pointer and you shone it out into space. You just clicked it for a second, and then you looked at where that light was going. A light year would be how far that laser goes in 1 year's time. And that distance would be 10 trillion kilometers. So a huge different distance. Let's look at this chart for a second here. So in this case, light. So if you look at the time that it takes light to go from the Earth to the moon, it takes about 1.3 seconds. So if you shone a laser at the moon, it would take about 1.3 seconds to get there. The time for light to get from the sun to Earth is about 8 minutes. So we'd say it's 8 light minutes. Now here's an interesting thing. The sun is going to be around for a long time, but let's say that it just somehow disappeared. If the sun disappeared, you actually wouldn't know about it for 8 minutes. Because the light that's reaching us on Earth right now, it was actually made 8 minutes ago in the sun. And it took 8 minutes to get to us. So now if you think about, what if you're looking at the star that's way, way further beyond our solar system? When you're looking at the star, you're actually looking at light that might have been created several years ago, or maybe tens of thousands of years ago. So when you're looking out at distant stars, you're actually almost looking back in time because that light has taken so long to get to you. All right, the time it takes light to get to Mars is about 12.7 minutes. So for example, we landed a rover on Mars a few years ago called Curiosity. And when that rover landed, it was sending information back to Earth, but it actually took several minutes for that information to get back, because the fastest you can send anything would be the speed of light. So even those messages that were coming back from the rover were delayed by, somewhere around 12 minutes. Right? So even though that rover landed, we didn't know that until 12 minutes later. The nearest star, so other than our sun, the next nearest star is actually 4.3 light years away. So if you sent a radio signal or you sent a laser beam towards the next nearest star, it wouldn't get there until 4.3 years later. So even if we were able to get to the nearest star, which we have no way of doing, it would take over 4 years just to send a signal back to Earth. Now, if you look at the Milky Way galaxy, the distance from Earth to the other side of the Milky Way is 52,000 light years. So if you shone a laser beam, it would take 52,000 years to get to the other side of the Milky Way galaxy. So this is starting to give you an idea of the scale that we're looking at, about how large space is and how empty it is. All right, so we're going to look at a couple little pictures here that kind of shows you, actually I'll show you one picture here first. So I was talking a little bit about where we've landed some of our rovers. So we have landed a rover on Mars. You can look up the Curiosity rover, and there's a lot of pictures that we've taken that are pretty neat to look at of the surface of Mars. The only other planet that we've landed on is Venus. So these are unmanned probes. So that was back in the 70s. We landed two landers on Venus. So that's the best picture that we have of Venus. Now, one of the benefits of exploring space is you also start to learn things about Earth. So Venus actually has a very dense atmosphere that has high amounts of carbon dioxide. And as we might remember, carbon dioxide is what is causing climate change on Earth. So on Venus, Venus also has a runaway greenhouse effect. So it essentially had a climate change event in the past. And by going there, we were able to learn more about that, right? And that's helping us better understand climate change on Earth. Now I'll just go through kind of a couple different pictures here, which shows you kind of the scale of the universe. All right, so let's start off by looking at a planet. We'll choose Earth, for example. All right, so we'll take that as, I mean, there are smaller things, right? There's our moon that's smaller. There's a bunch of asteroids that are smaller, but we'll just start with Earth. If we zoom out a little bit, the next thing you would have would be our inner solar system. So what are the planets that are near Earth? Here's our sun, right? The planets that are nearest Earth, we have Venus, and then Mars, and even closer to the sun is Mercury. And past Mars is this asteroid belt. It's a whole bunch of smaller objects. Ceres is one of the larger chunks. It's essentially just a large asteroid in the asteroid belt. Now, what is keeping these things in these orbits? It's gravity, right? So the Earth is constantly being pulled towards the sun, but it's also moving around it. So it continually kind of loops around as it's essentially falling constantly towards the sun. But it's going sideways enough, fast enough that it can just keep going, along with everything else that's here. Right? So gravity is what's holding these things in their orbit and making them move around the sun. Let's zoom out a bit further now. All right, so this part here, that's our inner solar system. That's the asteroid belt there. Mercury, Venus, Earth, Mars are all inside there, right? Now, a little bit further out, we now have some other planets, right? Jupiter, Saturn, Uranus, Neptune, Pluto. And beyond that is essentially another asteroid belt. Now notice the further away you get from the sun, the less light you have reaching there and the less energy you have reaching there. So as you're moving further out, it's getting colder and darker. Back in the 70s, we also sent out the Voyager probes, which we can still communicate with today. And they were sent out, they've now passed Pluto, so they're out beyond our solar system, somewhere around here probably. And that's the furthest thing that we've ever sent out there. They're both run on nuclear reactors, so that's how they're still functioning today, over 40 years later. But they are slowly running out of power. And they've taken 40 years to get there. All right, let's zoom out a bit further. All right, here's our sun. What we're looking at here are some of the closest stars. So the diagram, we're drawing it as a two-dimensional diagram, but it's actually three-dimensional. So if you look beside the names is the distance in light years. Proxima Centauri, that's the nearest star to us, the nearest other solar system, and it's over 4 light years away. And there's also Alpha Centauri, right, around 4 light years away as well. Now remember that most of these stars also have planets around them, right? Just like we have planets around ours. Some of them have a few, some of them have far more. But these are all of the surrounding ones. But once again, right, if you sent a message, or if you sent a laser beam to Alpha Centauri, it would take over 4 years to get there. Let's zoom out some more. All right, the Milky Way galaxy. This is now a collection of all of the stars that are near us, right? And at the center of our galaxy is a black hole, and that's what's allowing everything to orbit around that black hole and stay in this sort of shape. Now, once again, here's our solar system, right? Here are kind of the nearby stars, but all of these are all other individual stars. And around each one of those is possibly another solar system with many planets. The areas that are brighter, right, just means that there are probably more stars there, right? So there's more light being generated there. Not only are there stars and planets, but there's also clusters of dust and gases and things like that. But we can zoom out even further. All right, now we're looking at something which is the local group. So here's the Milky Way galaxy. But there are other galaxies nearby and other collections of stars nearby. So there's smaller ones that are near us. Over here is the Andromeda galaxy, the next closest galaxy. Right? In this case, 2.5 million light years. So if you wanted to send a message, or you wanted to send a flash of light to the Andromeda galaxy, it would take you 2.5 million years before it got there. What's in between it? Mostly nothing. Mostly a vacuum of space. But once again, each one of these galaxies has all of those individual stars in it. And we can zoom out again. All right, now we have a bunch of clusters of galaxies. And each one of those galaxies has all of those solar systems within it, and you can zoom out even further. This is now the local supercluster. So clusters of galaxies. And you can zoom out even further to the observable universe. So you can just think about the scale of what we're dealing with here, right? In terms of the number of stars and planets and solar systems out there.